Hello everybody, today I will be teaching you Floyd Warshall's shortest path algorithm. Unlike Dijestra's and Bellman-Ford's shortest path algorithm that calculates the shortest path from a starting vertex, Floyd Warshall calculates all the shortest pairs of paths. It will be able to calculate the shortest path from 1 to all its remaining nodes, 2 to all its remaining nodes, and so on. Both Bellman-Ford and Floyd Warshall can handle negative edges. However, when we talk about negative cycles, we should not try to find the shortest path, because after every pass we will end up with a better path. We have two graphs below. Let's see if we can find a negative cycle. The first graph has a cycle from 3 to 5, 5 to 4, and 4 to 3. We add up the weight of the edges and we get 6. This is positive, so this is not our negative cycle. For the next graph, we see that our cycle goes from 3 to 4, 4 to 2, and 2 to 3. We add up the weight of the edges and we get -2. This is our negative cycle. Let's now start a trace. We are using matrices to keep track of which paths are being updated. The number of matrices that we use depend on the number of nodes that we have plus 1. The plus 1 is from the initialization matrix. If we have a direct edge between two vertices, then the shortest path will be the weight of that edge. If we do not have a direct edge between, then the cost of this will be infinity. Since we have no self-looping vertices, the cost of a path from a vertex to itself will be 0. The nodes that we're talking about will be highlighted in yellow, and we will look at the direction of the edge to see if we do have a direct edge. We see from 1 to 2, we have no direct edge, infinity. From 1 to 3, direct edge, -2. From 1 to 4, no direct edge, infinity. 2 to 1, direct edge, 4. 2 to 3, direct edge, 3. 2 to 4, no direct edge, infinity. 3 to 1, no direct edge, infinity. 3 to 2, no direct edge, infinity. 3 to 4, direct edge, 2. 4 to 1, no direct edge, infinity. 4 to 2, direct edge, -1. 4 to 3, no direct edge, infinity. Now we're at k equals 1. That means we copy the first row and the first column from the previous table. We will now find our split points and then compare it to the split point if we allow ourselves to have an intermediate vertex. We are trying to update the shortest path from I to j, allowing vertex 1 to be an intermediate vertex. Let's start off by doing 2, 3. Now let's do 2, 3. We see our regular point 2, 3 and also our 2, 3 split up using our intermediate vertex. We want to see which path costs least, the one without the intermediate vertex or the one with it. We're going to find all of these values from the graph before, so k equals 0. Mapping those values, we see that we do have an update, because 3, the split point value without the intermediate vertex, costs more than the split point value including the intermediate vertex. So we update that point to 2. 2, 4, we're doing the same thing, retrieving the values from k equals 0. We see that we do not have an update. Infinity is not going to be greater than infinity plus 4. Same thing with 3, 2. We see we have no update. 3, 4, we have no update. 4, 2, no update. 4, 3, no update. It's important to note that we split apart our point and put our intermediate vertex between it, and then add those two new split points together to get our comparison. After comparing all the points from k equals 1, we see that the only point that was updated was 2, 3. Now we're at k equals 2. We copy the second row and the second column. We're trying to find the shortest path from I to j by allowing vertex 2 to be an intermediate vertex. I to j is the path on the graph. Once more, we're looking at the graph before it, so k equals 1. Going through the passes again, we get 1, 3, there is no update. Our split point before was better. 1, 4, no update, our split point before was better. 3, 1, no update. 3, 4, no update. 4, 1, now we see we have an update. The value for our split point using 2 as an intermediate vertex is better than not using it. For 4-3, we see we do have an update. Our split point using our intermediate vertex is better. After this, we see the only split point that gets updated is 4-1 and 4-3. Now we're in k equals 3. We're trying to update the shortest path from I to j by allowing vertex 3 to be used as an intermediate vertex. We're in k equals 3, so we copy the third row and we copy the third column. And once again, it's important to know, if you haven't seen this pattern, our diagonal is always going to be the zeros. You can pause here and see how these comparisons were made. After making these comparisons, the only points that we were able to find that were better using the intermediate vertex was 1-4 and 2-4. And now we're in k equals 4, trying to find the shortest path from I to j by allowing vertex 4 to be an intermediate vertex. You can pause the video here again and see if you can make these comparisons with me. We copied the fourth row and the fourth column. Looking back once again at the table before, k equals 3. After doing all these comparisons, the points that were better, including the intermediate vertex, was 1, 2, 3, 1, and 3, 2. I hope while we were going through this trace, you were able to find a pattern. We're choosing the smallest cost path between the split point and the split point including the intermediate vertex. The min function will return to us the smallest of both values. Let's talk about the runtime of Floyd Warshall's shortest path algorithm. Each pass that we do, we're generating a matrix that is dependent on the number of nodes in the graph. This is an array of n by n. With a 2D array, we know we need 2 for loops, one for the rows and one for the columns. Let's see what this code looks like. I have written out the pseudocode, and now let's break it down. The highlighted lines show the inner loops that are used to access the 2D array. Now we have the Floyd Warshall formula. We see that we are going to take the minimum, the split point, or the split points including the intermediate vertex, whichever one is cheaper. Now we have to generate our k's so we can create all the matrices that we did while going through the algorithm. The outer for loop for the k will make sure that we can check every single intermediate vertex that we have on our graph. Back to the runtime. We can see from the code that we have 3 nested loops, so our runtime must be theta of n to the third power. Thank you for watching this video. I hope this was helpful in understanding Floyd Warshall's shortest path algorithm.